We are going to conduct two experiments in order to test the gray mold fungus, Botrytis cinerea, for its resistance and sensitivity to the fungicide fenhexamide. This video covers part 1 and another video covers part 2. In part 1, we're going to test the fungus in agar plates, amended with various concentrations of the fungicide. In part 2, we'll test to see if the fungus can actually overcome the presence of the chemical on live plants and cause disease, or if the fungicide protects plants from botrytis. We'll be using two different isolates of botrytis. One is labeled B16 and the other is labeled B1728. On part 1, on agar, this is a very artificial way of testing a fungus's resistance to a fungicide. By trial and error, you find out the amount of fungicide that will completely stop the growth of the fungus, and that's called the EC100, or effective concentration that slows growth 100%, as compared to growth on no fungicide. Then you make dilutions of that amount of fungicide to get a range of inhibition so that you can find the amount that slows growth 50% as compared to growth in the absence of fungicide. And that concentration is called the EC50, or effective concentration 50. The EC50 and the EC100 are usually characteristic of a particular isolate. The concentrations you use in agar plates are usually very different from those actually sprayed on a plant in order to control a particular pathogen. Many times the concentration used on a plant is 10 times or more the amount that slows growth in an agar plate. But sometimes the EC50 can give you an indication as to whether a fungus is resistant or sensitive to a fungicide on plants. Resistance means that the fungus can overcome the fungicide on a plant and cause a disease, even though the fungicide is present. However, there are some cases where a fungus can actually grow on a high concentration of fungicide and appear to be resistant to that fungicide in agar, but it cannot overcome the label rate of the chemical sprayed on a plant. And so then you really can't say that it's resistant. So we need to test both situations. We'll test it in agar to give us a rough guess as to whether it's resistant. And then we'll test it again on plants treated with a label rate of chemical, and then make a final assessment as to whether one or both of the botrytis isolates are resistant to fenhexamide. Now, there are written details for both parts of the experiment in the Lab Report Resources folder of Angel. In part 1, we will use agar with no fungicide and agar with fenhexamide fungicide at concentrations of 0.002, 0.02, 0.2, and 2 micrograms of fenhexamide per milliliter of agar. And micrograms per mil is the same as parts per million, or ppm. We calculated how much fungicide needed to go in the agar. We melted the agar, applied the fungicide, mixed it in, and then poured the plates and let it solidify. And in the meantime, we grew B16 and B1728 separately in plates, and then used a sterile cork borer to cut plugs of the growing fungi from the plates. Then we used a sterile needle and transferred a plug of inoculum and put it fungicide down on the edge of the agar plate in order to start the test. We labeled the plate with the isolate number and the fungicide concentration and date. Once the plates were inoculated, we put them into a plastic bag upside down. If you incubate them right side up, you get a lot of condensation on the lid of the plate, and then it's difficult to see the fungal growth. So then we incubated the plates for 1 day, and then we used a marker and marked the curved edge of the inoculum block, and we used a straight line to mark the edge of the fungal growth. And we did that for each plate. Now you can measure the amount of growth in our virtual experiment by clicking and dragging the ruler, and drag the ruler over and measure the distance between those two lines, and record that amount of growth for day 1 for each plate. The photos are the same size so that you can use that single ruler to measure the distance on each plate. There's an Excel spreadsheet provided for you in the Lab Report Resources folder where you can enter the data for each plate. Now, if you look at B16 photographs for day 1, it looks like B16 grew more on the 0.002 micrograms per mil plate than on the plate with no fungicide. And in fact, that's exactly what happened. That's a phenomenon called hormesis. And in hormesis, a small amount of a toxic material can actually stimulate the growth of a particular organism. Now, you're very familiar with hormesis if you've ever taken any kind of a medicine, because in most cases, medicines are very toxic chemicals if they're taken in high amounts, but they can be very helpful if taken in low amounts. So, for example, whereas 1 aspirin is good for you, 100 aspirins probably is not good for you. Now, hormesis does not occur in every isolate or to every chemical, but this is a good example here. After 2 days of incubation, we marked the plates again where the fungus had grown out from the inoculum block, and you need to measure all the growth on all those plates and record the data in the spreadsheet. Finally, after 3 days of incubation, we mark the plates, and you need to measure the growth from the edge of the inoculum block to the edge of the growth after 3 days on each plate, and record that information in the spreadsheet. Now, you do that for both isolates B16 and then do it for isolate B1728. One way to look at the data is to graph the millimeters of growth on each plate versus the days after inoculation for each isolate, and then draw a line for each concentration of fungicide. Now here, this is just an example, and it's not based on any data from the experiment. It's just to illustrate one way of looking at the data. So using your measurements, you can create a graph like this for B16 and another graph for B1728, plotting the growth of those isolates at each fungicide concentration against the days after inoculation. And you can do that with the Excel spreadsheet. And if you're not sure how to do that, if you look in the written directions, again, those directions are in the Lab Report Resources folder. I explain exactly how you can take that data and use Excel to create the graph. Another way to analyze the data is to compare the amount of growth on a particular concentration of fungicide versus the amount of growth of that isolate on an agar plate with no fungicide. And that's called the percent relative growth. So the percent relative growth equals the growth at a fungicide concentration divided by the growth on 0 fungicide times 100. So for day 3, calculate that number for each isolate and each fungicide concentration. Again, record those numbers and the percent relative growth calculations in the Excel spreadsheet that was provided. In the percentages shown here, these are just an example and they're not based on any actual measurements. So you fill in the Excel spreadsheet table with your measurements. In this example, you can estimate that the EC50 falls somewhere between 0.002 and 0.02 micrograms per mil of phenhexamide. So you should do that for your two isolates based on your data and estimate the EC50 for where it falls for each of those two isolates. Then you need to answer a couple questions. So based on this experiment, which isolate do you think is more sensitive to the fungicide? In other words, which one is inhibited the most? Or which one appears to be resistant? Do you think that one of the isolates should be said to be resistant to phenhexamide, meaning it's not inhibited significantly by phenhexamide? Now, as I said in the beginning, it's one thing for a fungus to be inhibited by a chemical in agar, but it's quite something different on plant tissue. So before we can really say that an isolate is truly resistant to a fungicide, we need to test that isolate to see if it can cause disease on a plant that's been treated with a chemical. The plate tests that we've done here give some indication of resistance, but it actually has to be verified on plants using the label rate of fungicide. And that's what we're going to do in part 2 of this lab experiment.